You can use WebMO to calculate the molecular orbitals of a wide array of molecules, but there's more to WebMO than just molecular orbitals. In this webcast, I'd like to point you to some creative uses of WebMO beyond the simple HOMO-LUMO usage that we've seen, and also provide you with a guide for embedding WebMO results into your wiki page. Basic embeds of calculated molecular orbitals are pretty easy to do. All you have to do is navigate it to a completed molecular orbital job, scroll down in the View Job window until you see these orange disk icons in the molecular orbital table. Click any one of these icons to download the job file corresponding to that job. This now needs to be attached to your wiki page in order to be opened on the internet in the JMOL interface. So return to your wiki page, go to Edit Attachments, and attach it in the usual way. With the .mo file attached, remember to right-click it and click Copy Link, and then return to the JMOL interface and select Load Structural File, pasting in the link that you just copied. You'll see the molecule that you calculated on appear, with no MOs on it. To add MOs to it, you need to go to the Objects Orbitals menu. Once here, you can load molecular orbitals by typing either a number, HOMO, or LUMO into the text box here. For instance, if I type HOMO, you'll see the highest occupied molecular orbital load when I press Enter. And there it is. We can then save a state file and embed it in the usual way. WebMO can do a lot more than just molecular orbital calculations. One of the coolest things it can do, especially if conformation is important to your molecule, if for instance it's a ligand for a protein that does catalysis by strain, as we talk about in lesson 29, then the coordinate scan that WebMO can perform is going to be invaluable to you. Using the coordinate scan, you can see how a conformational change translates into a higher energy for more strained conformers. To do a coordinate scan, the very first thing you'll want to do is optimize the geometry of your molecule. Click on the Optimize Geometry job, and then click New Job using this geometry. At this point, you want to specify exactly which bond you want to rotate around. To do that, click Open Editor, and then select 4 of the atoms that define the dihedral angle that you're interested in. In this particular case, let's say we're interested in rotation about this central bond. To specify that this is what we'd like to vary, what we need to do is use the Adjust tool, which you can get to by clicking the mouse icon here, and then selecting the 4 atoms that define that dihedral angle. So we'll start with one of the hydrogens here. We'll hold down Shift, click the carbon, still holding Shift, click another carbon, and then finally another hydrogen. And then we can select Adjust Scan Coordinate, and you'll see the Scan Coordinate dialog box appear. Now let's say we wanted to start at 175 degrees and we wanted to rotate around to negative 175 degrees, so roughly 360 degrees, and let's say we wanted to do that in 10 steps. The type dropdown refers to what happens to the rest of the molecule as you rotate. If you select Optimize, then WebMO will optimize the geometry at every step. If you select Rigid, then WebMO will leave the rest of the molecule alone and simply calculate the molecular energy at that dihedral angle, leaving the rest of the molecule the same. Let's go ahead and select Optimized and click OK, and you'll see the key bonds highlighted here in gold after you're done with that. At this point, we can just close the editor window and then begin the job. You'll want to make sure it's a MOPAC job. You'll want to make sure that coordinate scan is selected, and for the level of theory you can use either PM3 or AM1. AM1 takes a little less time, so let's use that. And then finally you can click the forward arrow to finish off the job. After about a minute or so of running, we'll get to a results page that looks like this. So nothing's really changed with the structure yet, but if we scroll down, we can see that the bond order has been calculated, and the coordinate scan table gives you a list of the dihedral angles and the corresponding energies. This may not look like much to you now, but you'll notice above that we can actually run a movie of the geometry sequence and look at what happens to the energy as we vary the angle. So if I set this to loop and then hit the little film button here, you'll see that it's looping through the various conformations and showing us the energies at the bottom of the window there. To get a more graphical representation, if you scroll back down, you'll see that you can select the magnifying glass in the coordinate scan table, and here's a graph showing us the energy as a function of the dihedral angle, or the coordinate. How you translate these results to your wiki page is in some ways up to you. There's no efficient way that we know of yet to get a movie like this onto your wiki page. However, embedding a graph like this into your wiki page would be as easy as saving a screenshot of this and then embedding it as an image into your wiki page. Remember that you'll want to make it clear with text and possibly other images what this coordinate scan graph is referring to.